Okay, good evening, gentlemen. So there's no lady, gentlemen. Welcome to this month's technical presentation for the Engineers Related Course Regional Group. And on behalf of the group, thank you everyone for participating in this event. For today, we have Professor Andreas Öchsner, which is from here, from Griffith School of Engineering. And today, Professor Öchsner will talk about the novel lightweight material, which is hollow sphere structure. And according to Andrea, he will have a few slides just to introduce himself. So I'm just going to hand over to Andreas to talk about himself. Okay, thank you.
Okay, thanks for the introduction. Welcome at this time for my lecture. Are you sure? We should continue?
Sorry?
You're 5 minutes early?
That's okay.
That's okay.
Flexible.
Okay. Yeah, I took some notes from drink and I prepared something on myself. Well, I'm from Germany, 43 years old. I studied aerospace engineering at the University of Stuttgart, and the traditional academic structure is quite different. So I had a diploma degree. The diploma degree in Germany is something equivalent to a master's degree in Australia. So in the traditional structure, we would have a 5 years program, which would incorporate a research component. So basically, the honors would be included, but there was no distinction between masters and bachelor and honors or without honors. 5 years full-time study, that's it. Nowadays, everything changed because of some European agreements. Nowadays, you find in Europe everywhere bachelor master's degree. Okay? And all the national European states had to adopt this system, which makes the exchange transfer of students much easier. But to be sometimes careful what means a diploma degree, it can mean quite different things in different countries. So the diploma degree in Australia is completely different than a diploma degree, for instance, in France or Germany. After having a diploma degree, I moved a little bit further from Stuttgart to the south to the University of Nuremberg. There was employed as a teaching and research assistant, again, something completely different than Australia. So PhD students in Germany are contracted as researchers. If you have any questions, you can stop me anytime. So that's quite different to Australia. As a PhD student, you get employed, you get paid, and basically it's your own problem to do your PhD. Well, after this, I'd like to go abroad. And one offer was going to Singapore, to NUS, National University of Singapore. There I got an offer as a Lee Kuan Yew postdoctoral fellowship. It was an international opening, and there were 2 places. I got one. And 50% was a research fellowship. I don't know, it sounds a bit strange to me because I applied for something, then they offered something 50-50%, and it was too far away, so I decided not to go to Singapore this time. Instead, I stayed in Europe. I moved from Germany to some warmer countries in Europe. I moved to Portugal, and there was appointed as assistant professor. And in the research unit, as head of the cellular metals group. Quite interesting, the structure. So the departments are solely responsible for teaching activities. So the department would have basically not much funding, because for teaching you don't need much. And parallel there would be a research unit, and the research unit would have a major budget and a research funding. Some people would be employed only in the department for teaching activities, and some only in a research unit, or you could have a double appointment. Sometimes it's even the same building, the same persons, but formally it's quite separated. there's a unit only responsible for teaching activities, mainly no budget, except to run the department, and then the research units. After spending 4 years in Portugal, I thought it's time to move on or give me a better job. So there was no better job. Then I moved very close to Singapore, basically to Malaysia, to the south of Malaysia, so just across the border to Singapore. And I was first appointed as visiting professor because the contract could be issued by the university, and after a few months they appointed me as professor because the contract had to go through the ministry. I spent there roughly 7 years. During this time, I was appointed at the University of Newcastle as conjoint professor, and I started intensive cooperation with them. And in 2010, I got a higher doctorate degree. In Australia, you have, after the PhD, either a DSc, a Doctor of Science, or a DEng, Doctor of Engineering, an academic degree, a research degree, awarded after the PhD. In Europe, Germany, France, Eastern Europe, you would have something similar. That would be called a habilitation. So after having a doctor degree, you would have one more academic degree, basically to stay in the academic pathway. And you would call it habilitation. It's again, it's slightly different in Australia. It's a pure research degree. So the DSc or the Eng in Europe, it would be rather a formal license to teach. Because in Europe, only the professors would teach. And the formal license in the old system would be the habilitation. So a doctor would be not sufficient to be allowed to teach regular courses. After Malaysia, well, since January, I'm now with Griffith University, and I was appointed professor and head of the discipline mechanical engineering. Okay, which research fields I'm covering? Basically, it's experimental and computational mechanics, the whole field. I worked a lot with structured materials, and today my lecture will be a little bit focused on cellular materials. Other research fields are plasticity, damage mechanics, thin structures and interfaces, and adhesive technology. And in this research field, published roughly 360 publications, and it's around 1,400 citations. Well, in addition to these research activities, I thought a lot about how to introduce computational methods to students, especially based on the experience in Malaysia, where students are not good. I came up with a new approach to teach finite elements just based on one-dimensional elements. I have this not in my course. In my course, you must go through all 2 and 3D elements. But basically, here the idea was we reduce mathematics to minimum and introduce different field problems, different finite element approaches, but only based on one-dimensional elements. Because mathematics is quite simple, and we can skip some complicated notation. Yeah, sorry. You must go through everything. And there was an extension of this approach, rather related to the nonlinear material behavior, and that's a book with around 600 pages, a few days ago published. What else? I'm quite heavily involved in some editorial work. I have a whole book series by Springer on advanced structured materials, so everything where not only the material, but in addition the structure defines the material properties is welcome here as a contribution, and we have actually, I think, over 40 books published here. Second editorial work is related to a new book product by Springer. It's called Springer Briefs. These are small booklets up to 125 pages, and the publisher tries to have some emerging topics and quickly published in a quite short time. Also have the journal where I'm serving as editor-in-chief. It's called Continuum Mechanics and Thermodynamics. It's quite a traditional journal, and we're looking here for some fundamental developments. Maybe new material laws, new solid mechanical description, and not rather applications. I'm organizing since a few years. Since 9 years, a conference related to applied mechanics. And since 11 years, conference rather related to material science. Next year, there will be 2 conferences in Germany. Okay, this was the short introduction. Now let me come to the technical presentation. I will start quite slowly with some just pictures, so easy to digest. There's a part related to continuum mechanics, so let's rather address the mechanical engineers, maybe civil engineers working in applied mechanics. To show to the students it's important to know the derivations. It's not just for the sake of derivations, you really can do something when you are able to derive equations. And I will show you some experiments, some numerical simulations related to these derivations. Okay, what's the idea for metal forms? Well, use of cellular materials, it's a basic principle which we know from nature. So for all weight-carrying structures, such as bones, we know that's a lightweight material, that's an optimized lightweight material. And here on the left-hand side, that's a micro CT scan of a human bone. And exactly this idea of the structure was transferred to a metallic structure. We are made of aluminium in order to provide these outstanding properties to engineering applications. Well, this idea, it's already quite old. We know this from synthetic foams like isopor for insulation purposes. But around 10 years ago, what was new in the developments was to use metals or metal alloys to produce these forms. And well, the idea is if we incorporate multifunctional applications, we should be able to replace traditional engineering materials and offer better properties. A few examples how this could be used. Here on the top, these are sandwich structures with different core materials, so that's an aluminium foam. And due to the manufacturing process, there is a solid phase sheet produced. That's a different type of sandwich structure where some regular cellular core is used. And the lower picture is a hollow profile stiffened with a metallic foam, and the idea is to use this as a shock or crash absorber. And the stiffening, which is quite light, changes dramatically the bucking behavior. So you can somehow introduce a way to guide the energy absorption in the case of the crash of the material. So weight practically not increased, but the energy absorption capability dramatically increased. A few other pictures, how cellular materials can be used. Of course, for casting, the idea is all the time the same. I have outside a solid phase sheet and inside a cellular core. Let's have a look more in detail on such a structure. To stiffen the profile, and where this idea is coming from, well, the idea is coming from nature. So if you look on a bone, you see exactly the same idea, but the idea was copied basically from nature. So we have outside a solid phase sheet, and inside a certain type of cellular structure. What's now still the difference? Well, nature optimizes everything. So here we have a certain gradient. So you see here this is a much denser area. So here we have a much lower density of the trabecula. And well, nature optimizes according to the load pass or the applied load. So here we have still some kind of uniform density, but also this idea is taken into consideration, and these materials are called functionally graded materials, where we have properties or densities varying over a certain length and adjusted according to the needs of the application. What's the problem with the previously shown structure is they are still quite heterogeneous. So it's some kind of arbitrary network. And this makes it very difficult for engineers to simulate the properties and guarantee properties. And therefore there were different developments done in order to produce cellular materials where the properties are much clearer defined and can be guaranteed. Because if I cannot guarantee the mechanical properties, no one will apply it. And one attempt was so-called syntactic foams. Well, it's a quite interesting material. It's based on aluminium spheres embedded in a magnesium matrix. So two different materials form a composite material. And what is here used is the different melting temperature of these two alloys or metals in order to cast it. So that's quite fascinating. So a metallic composite material based on two different metals. Well, this brings the idea further. So-called lattice block materials, they were introduced or were supported by the US Ministry of Defense in order to have a periodic structure where it's absolutely clear what are the properties. So basically here people that do simulation are very happy. It's easy to simulate the structure. On the other hand, it's much more expensive than these arbitrary structures. But for military applications, the costs are never the problem. Just the performance of the material is what counts. Price is never important, especially for aerospace applications in the military. Now it comes slowly to the materials we have worked for several years, which are called hollow sphere structures. What's the idea? There's a basic unit that's a hollow sphere made of maybe an iron material. And these hollow spheres can be joined in different ways. And this gives you different possibilities to tailor your properties on a macroscopic level. Well, that's a picture where the hollow spheres are soldered. And that's a picture where the hollow spheres are adhesively bonded in certain points. And using different joining technologies, an engineer would be able to offer different properties according to certain requirements from the engineering design. But not only the joining technology, also the basic structure. This means the diameter of the spheres, the wall thickness of the shell, the material, could be iron, it could be magnesium, it could be titanium, gives you a lot of possibilities to create a tailored material according to certain needs. So there's not a single structure which we would say, that's the best. No. You have a whole range of properties, and basically, according to the requirements, you could offer it. So maybe the soldered or glued structure would be better. And these samples that go now through the auditorium, it's an iron form. Wow, this basic sphere is an iron material, but it's so light, but it's extremely stiff. It's highly interesting. So a lightweight material, an extreme lightweight material, which gives you the required properties of stiffness and strength. Here on the left-hand side again, partially fluid, so this is zoomed in. We have the spheres, and in certain points, the spheres are adhesively joined. And here on the right-hand side, it's a different idea, taken from classical composite materials, where we normally would have fibers embedded in the matrix, and the idea was here to embed the spheres in the matrix. And the interesting thing is, comparing properties between these two configurations, so just partially joined together or completely embedded, the interesting is the weight doesn't change so much, but the macroscopic properties are completely different. And again, there is no better or worse, it's just a variety that we can offer for certain problems. And as a final joining technology would be sintering. So basically it would be only one material. You can imagine this like baked together. So there's no adhesive, there's no soldering agent, just this iron alloy. So what I showed you was soldering, adhesively bonding, completely embedded in the matrix, and sintering. As different joining technologies. And then you think about the different base materials of the spheres. You have a quite huge variety to produce certain properties. Okay, so this was the easy part. I still like to show to the students that it's important to work with equations, that you're able to derive equations, and that you can get something from this derivation. Let's start slowly. Well, the application of these materials in any load-carrying application requires that basically engineers can predict and guarantee the properties. If an engineer cannot guarantee or predict properties, no one will use it. No designer will use these materials. And in the scope of these cellular materials, mechanical properties are at least approximated as a function of the relative density. And the difference to classical dense materials is that the microstructure, basically the pores, and the material itself defines the properties. So for a classical material, the properties are only defined by the material itself. For the structured materials, it's material plus structure. And we can keep the material the same and change the structure, and we get different properties. That's the interesting with these materials. What is shown here, that's a classical compression test. So uniaxial, you simply compress the specimen. And then, again, it's a quite different behavior to classical dense materials. So basically on the vertical axis, the stress, horizontal is the strain. We have some kind of linear elastic range at the beginning. There's a certain transition region. We have a quite horizontal plateau. And at the end, that's the densification of the material. Why this is interesting? If you think about one of these previous pictures where a hollow profile was stiffened with the cellular material and possible application could be a crash absorber. Well, for crash absorber is important basically the energy that we can absorb. So the energy is the area under the stress strain diagram. And if the stress is not too high, basically if you think about a car crash, it would mean the accelerations are not too high for the passenger. Okay? So there are different ways to absorb energy. You could have basically a very stiff material, but this would mean it deforms not much and the accelerations would be very high. Or rather more some kind of soft material where we have this plateau region where the stresses are not too high, but the same energy can be absorbed because of the length of this plateau and the accelerations would be much lower in the case of an accident. And well, that's the configuration for this test, basically a symmetrical sample compressed and we would get this. On the opposite side, the stress strain diagram for a tensile test, so that's the compression test, which would be interesting for a crash absorber. But if you would do a tensile test, it would rather look like a classical engineering metal. So we would not see this plateau region in the tensile test. So it's a completely different behavior under tensile and compressive behavior. And the compressive behavior is especially interesting for the energy absorption. Okay, who's a mechanical engineer? Peter. Yeah, but that's something for you. The rest, no mechanical engineers. The question is only how quick I should go through the equations. So if there are no mechanical engineers except our guys, it makes no sense to go in detail, and I just will roughly summarize the ideas. No mechanical engineers? Okay, so I go a little bit quicker through the equations. For the students of the finite element course, also these materials are described by Hooke's law. Okay, now 3D, remember 3D elements, 3D Hooke's law. It's used for the elastic range, our standard approach. For the plastic behavior, we will need our three equations as we had this in the lecture: the Griffith criterion, flow, hardening law, everything 3D. Okay, so from the continuum mechanical point of view, we need this as a first start. These four equations. What's not so specific with cellular materials? It's quite common to sketch a diagram where the horizontal axis would be the hydrostatic stress. This means, or hydrostatic stress you can imagine as any body which is under the water. So we have a stress from all sides the same. That's hydrostatic stress. And on the vertical axis, that's the Von-Mises stress. Okay? And in such a diagram, I can identify simple, basic experiments like a uniaxial tensile test. On the vertical axis, it would be pure shear test, torsion. On the horizontal axis, it would be isostatic tension. This would mean I would elongate the cube in all three dimensions with the same magnitude. And if we are doing now a tensile test, well, we start here in the origin, no load, we increase the load, and we record the initial yielding of the material. But this gives us only one point. So the uniaxial tensile test or compression test, if you assume it's symmetric, gives you 1 point. This would be sufficient for our classical methods, where we use Von-Mises or Tresca. But these cellular materials, they're much more complicated. They are sensitive to the hydrostatic pressure. So we must characterize the shape of the yield surface in this diagram based on different experiments. But just the tensile test is not sufficient. I must add an experiment. For instance, I can do the uniaxial compression. Why? Well, if I have a universal testing machine, I can do the tensile test, I can do the compression. And that's standard in any materials. So basically, these 2 points are not so difficult to get. So the circle indicates the initial yielding. Transition from elastic to plastic. But with 2 points, we have a problem. I can also then connect 2 points with a straight line. Okay? So if we assume that the yielding under compressive and tensile load is the same, if we would assume a straight line, we would end up with a Frommesis yield condition. But it's not like this. Frommesis yield condition is only appropriate for classical methods. As soon as we have a cellular structure, it works no more. We must have an extension of the Frommesis yield condition. So we need one more experiment at least, or even more experiments would be appropriate. Well, one option could be pure shear test. It sounds very simple, pure shear torsion, but to realize it, you must have a very specific machine, or modify a universal testing machine in order that you get a shear test. It's not so easy. So basically, moving from these 2 points to the third point could mean you need a completely different equipment to do the materials testing. And different equipment is expensive. Okay, but basically that's the idea. I must realize some multi-axial stress states in order to characterize the yield condition of this material. Because the measures of press does not work. The further problem is, if we only think about the elastic range, and if I would like to determine 2 properties, okay, typical knowledge questions for a test. How many material parameters I need for hooks or in 3D case? I need 2 parameters. Young's modulus, okay, we could do the tensile test. For classical materials, we could get from the tensile test even a second elastic constant. We could take such a flat specimen, we could glue a strain gauge on it, and measuring the elongation in loading direction, perpendicular to the loading direction, we could get a Poisson's ratio. So for classical dense materials, straightforward. But if you look on the sample that is with you, it's not so easy to glue something on the surface. Okay? Because it's so heterogeneous. Or if you think about these open cell structures, there is no way to attach any strain gauge. Or an extensometer is the same way. Same problem. How to attach to the surface, which is not smooth, which is not flat, which is not dense, an extensometer. Very difficult. So just the task to get the elastic properties is very difficult for these materials. So even if we forget the plastic range and just think about an elastic simulation, we have the problem to get the second material property. You can do the tensile test, the compressive test, to get Young's modulus, but the second one is very difficult. Okay, I will make this part a little bit shorter. Classical yield condition, for instance, Frommesis yield condition, are composed of 2 parts. One is some kind of equivalent stress, where all the stress components goes inside, and I get a scalar value to compare with an experimental value, like tensile yield stress, shear yield stress. Okay? And what's now new with these materials, I must extend this yield condition by something which incorporates the hydrostatic stress, and this hydrostatic stress is weighted with certain functions. And that's the difficult part. The difficult part is to get this dependency on the hydrostatic stress, and one strategy was shown on the previous animation where different multi-axial stress states must be realized. So the difficulty is definitely to find this influence. What is much easier to get this other parameter, which could be uniaxial tensile test, shear yield stress. So the challenging is to characterize how this material is dependent on the hydrostatic stress. Make it short. There are 2 ways, or 2 proposals. One is called a plane strain test. So plane strain test would be, I take this sample, I compress it, uniaxial compression, but I keep the deformation in one direction is 0. So I constrain it to 0. The third direction is free. This would be a plane strain test. The other proposal is called axial compaction, where I compress the specimen, but both other sides are constrained to 0. Why we need this test? Because we need some multi-axial stress state in order to characterize the influence of the hydrostatic pressure. So it's not just a classical uniaxial compression test. No, this would be uniaxial if it's ideal. We need something where we have more stress components acting. And these are 2 proposals. Using these proposals of experiments, well, without following these equations, we get some relationship where we can characterize this influence, alpha, which weights the hydrostatic stress based on measured values. And when we simplify this to the elastic range, again, I skip a few equations for the mechanical engineers, there are two very interesting results obtained. One is for the plane strain test. So the plane strain test was, I have the sample, I compress it, in one direction I constrain to 0. And just by measuring the ratio of these two stresses, the one stress to compress and the other stress to hold, basically constrain the deformation to 0, I get Poisson's ratio. And this is completely different than the classical measurement of Poisson's ratio. The classical measurement of Poisson's ratio would be based on a strain measurement. So I need some kind of extensometer, I need a strain gauge. Here, it's a force measurement. Okay? The stress is a force. It's basically a measurement where I don't need to attach something to the surface. So the load cell would be something else. It's a completely different approach. It's quite tricky and simple. The other test has also an interesting result, the actual compaction, where I compress a specimen and the other two directions are constrained to 0. And then by measuring the slope, basically how I compress the sample, so stress over strain, I get a relationship which depends on two elastic constants. That's still not so interesting, but Young's modulus could be determined with a classical tensor or compressive test. And then by doing this actual compaction, we may imagine it like a cylinder which is compressed in a tube, and just measuring the slope, that's not too difficult. Because it's just a load cell which measures the force and a strain measured maybe by recording the displacement of the cross set of the machine. Then I have a relationship which may provide a second elastic constant. Okay? And these two simplified results, where a few equations were skipped, solve the problem how to provide a second elastic constant for these materials. And because I cannot attach an extensometer here, I cannot glue a strain gauge on it. Well, these are theoretical derivations, so you need to know something about continuum mechanics, you need to know the theory of plasticity, and you get this result. Okay? So if you ask me why I need all these equations, this is one answer. Okay, and then either you can do the test or you can do the simulation. Different results. I used some kind of model structure to see if it really works. So we produced some kind of artificial cellular material where the pores are nicely periodically arranged hollow spheres, or spheres in that sense. And then we loaded the sample in compression, and we recorded the stress required to constrain the displacement to 0. And then, well, that's the stress to compress the sample, that's the stress to hold in one direction the displacement to 0, and we get at the very beginning a straight line where the ratio is equal to Poisson's ratio, and then there's some transition to the elastic part. And based on these results and the involved theory and the equations, we can calculate this factor alpha, which weights the influence of the hydrostatic stress in the yield condition. And that's the yield condition. So this is something what we had for sigma 1, sigma 2, very similar. Okay? Or basically, this would be rather corresponding to the shear stress, normal stress representation of the yield surface. So we had this ellipse shape for Mises and Tresca. It's quite similar, just for more stress components plotted. Well, the question is now how to realize this plane strain test to compress and to hold the displacement in one direction to 0. It's from the theory very easy, but the experimental realization is not so trivial. One way could be to use such an equipment. That's a biaxial testing machine where you can load specimen in one direction and perpendicular. And this was done by a student in the scope of a master thesis to design a mechanical test. And we built this machine, This was not a part of the master thesis, but all the drawings were done within one master thesis. And then we tried to use this machine to verify the theory and see if it really works. And how to start? Well, because we don't have any reference value for this material. So whatever we measure, how to compare it. Okay, you can measure something, but you don't know if it's whether the good or bad value. So how we started, we used some materials where we know the properties. And in order not to harm somehow the machine, we started first with some plastic material. So that's PMMA. One of my colleagues measured the elastic properties in the classical test. And then we used this PMR sample, which is transparent and was former times used for fracture mechanical investigations. And we obtained a certain Poisson's ratio. This correlated very well with a classical tensile test. And the other test was we used some kind of rubber-like material. So here is black material in the center. And then we got a Poisson's ratio, which is close to order 5, which is the value that a rubber material should take. And then we used the model structure of a cellular material and a closed cell foam. And we got the following results. But the problem is we do not know if this is correct or not. But at least we did some kind of benchmarking with materials which we knew. And I think that's a good approach how to validate your results. Nevertheless, these few examples where we drilled from precise holes inside to get some kind of artificial cellular material, we transformed this in a very simple computational model and we simulated the experiment. And well, this diagram shows as the solid line the experiment, and the other lines are different approaches of the computation. And that's the diagram for this factor which weights the influence of the hydrostatic stress. Again, the solid line here in the middle, this is the experiments. The other two lines are two different computational approaches. So not too bad. So this was the plain strain test, and the other test which was post-axial compaction, we didn't realize as an experiment, but we made a few simulations. So this would be the test where I compress the specimen and I must hold the displacement of the other two sides equal to 0. Or realized as an experiment, you can imagine as some kind of tube, and we have a cylindrical specimen, and we compress the cylindrical specimen in this tube. And then what we made, we assumed certain parameters, and we assigned these parameters to the material and followed the experimental procedure and tried to evaluate what was expected. And doing simulations, it's nice, it's easy to change certain configurations. So basically this is a more rotational symmetric model where we assumed the tube outside to be perfectly stiff. That's the simplest approach. Because the cellular material is much softer than a steel tube. So the most simplest computational approach is to assume that the tube outside is not deforming. Okay? On the other hand, we can model the tube outside and we see how the results are changing, the evaluation. And then we can evaluate according to this procedure the material parameters. Using simulation, you can also change very easily the ratio of the stiffness of the tube and the cellular material inside. And it's possible to check how accurate is the evaluation approach. And of course, the result is that the softer the cellular material is, or the stiffer the tube outside, the better the evaluation works. Or what is sometimes interesting, when you compress something, well, there should be some friction between the walls. So we made a simulation where we assume different frictional coefficients. And we checked how this influenced the evaluation of the results, because this basic evaluation doesn't consider any friction. One way to reduce the frictional influence would be this double configuration where two pressure feet are compressed from both sides, so you have less friction than configuration with one pressure feet. Solving the problem for a second elastic constants could have also some other applications, but that's more known from civil engineering. There are people that are using triaxial tests, where we can compress from three sides, mostly concrete specimens, and the evaluation of such a test, at least in the elastic range, would give us the Weyert modulus. So this would be an option to measure a second elastic constant. But of course, we must have this equipment. And I'm not sure that this is cheaper, a triaxial machine, than a biaxial machine. So it's quite important if you investigate new materials, the basis of continuum mechanics. Okay? So if you cannot evaluate in a classical way the second elastic constant, you must come up with other ideas. And this works only when you have the knowledge of continuum mechanics. Either doing a triaxial test or a biaxial test. Yeah, we published a few books on this. What are challenges? Challenges are, when we're using these cellular materials as a core of the classical sandwich material, the challenge is how the interface goes. Basically, where the cellular core is attached to the full dense material. And for a computational approach, the simplest approach would be to assume a perfect bonding between the cellular core and phase sheets. But that's not reality. That's a simple model. Okay, modeling means all the time simplifications of the reality. And that's a rough simplification, but it's one approach. If you want to have it more accurately simulate, you must think about, well, how this interface really looks, how I can model it. Or what you see here is, that's a typical approach. We have a certain structured material, and we do some kind of homogenization, where we represent the structured material with classical elements which have the same properties. Again, that's a very simplified approach. More accurate would be maybe to do a CT scan and really come up with a computational model where the model has the same geometry as the real specimen. So that's not a geometry of the real specimen. Okay? But it's a simplified modeling approach where we try to assign to these elements the same properties. That's the common approach how to start. And then we would refine. And maybe at the end we would say, okay, let's take a micro CT scanner to have exactly in the computational model the same geometry as the real specimen. But that's a very simplified model how we can start to look at this. What could be different? Further works. Well, still, the simulation of sandwich structures is not completed. There's a lot of work done with some kind of simplified periodic cell structures, where this arbitrary arrangement of the cells is broken down to a periodic arrangement, as we know from the atomic lattices, like face-centered cubic, body-centered cubic, hexagonal. So these are modeling approaches, and in order to reduce the complexity of the real structure. Well, I spoke about applications as crash absorbers. The crash absorbers requires a completely different description of the theory. We have large deformations, we have large strains. We must have certain knowledge of continuum mechanics. And what we have in the lecture, or what I have shown, is basically limited to small strains. Well, and a lot will be, or is done, or is going on in the direction of biomechanics. Okay. 35 minutes or 40 minutes. Thank you for your attention. Please, I'm happy to have your questions.
Questions?
Yes.
You can measure the movement of the place of the structure with some sort of grid rather than a strain gauge, a fringe grid or something like that.
Sure, but these methods to optically measure maybe the displacement or the strain field rather requires, in the traditional approach, a flat surface and where you have a pattern. It would be interesting to check if this pattern, which is given by the structure, could be used to optically measure the strain field, yes. But nevertheless, it's not so trivial. There were approaches done where people try to simply glue a foil, plastic foil, on the surface to produce a flat surface which is not stiffening the material. Yes. Different ways, but it's not easy. It's not easy. Even with optical methods. Yeah, with a video extensometer, yeah. But the classical approach requires a flat surface with a pattern. That's not so flat and not so right pattern. So basically we would have a white background, maybe some black dots. Then we could use a video extensometer. Or maybe a regular printed pattern on this specimen. it's difficult. Yes?
Of course, the other way of assessing the properties of the material are make prototypes and break them.
Sure.
And,
that's all the time the best approach to the test. But at the end of the day, we try to have only a minimum number of tests and then to use computational models because it's much cheaper. But of course, the first characterization will be done by testing. Yes. But testing and getting a second elastic properties is difficult. It's difficult. And that's the beginning of the deformation range. So the elastic range is at the beginning, and then we have a very complex elastic range, which requires much more experimental setups to determine this range. Yes,
well, it appears that the material has particularly good characteristics in shock absorption. Now, I had many years ago the problem to protect nuclear power stations against the impact of a phantom jet, 25 tons at 800 kilometers. We developed the wall 2 meters thick. I can tell you how we reinforced it. Could you tell us how much better that material would be in the shock absorption in that dimensions?
Yeah, for atomic power plants, the question is different than with cars, right? You want to have something very stiff, and it doesn't matter what happens with the airplane or the pilot.
That's right.
So you can make it really stiff.
About.
Yeah, we forget about it. So it's rather the task to make it extremely stiff. For a car accident, it would be completely the wrong approach. For a car accident, we want to have something that can smoothly deform and absorb the energy on a low stress level in order to guarantee that the driver will survive. But it would be not the right material for this. If you ask me how to protect the power plant, I would make it very stiff. Not with this material.
No, but you're wrong. Because the impact load cannot be transmitted to the interior of the building because the reactor is not allowed to move a millimeter. So I need the shock absorption.
Sure, but if you have an airplane or the mass of the engine would be representative mass for an airplane impact, I don't think it's stiff enough or soft, or maybe it's too soft for this mass.
You can't get the equivalent to high-strength concrete.
Never.
Never.
It's a lightweight material. you don't need in your applications a lightweight material. Okay, so the interesting properties is not the stiffness, is the stiffness normalized with the weight, and you don't need this. So I would suggest completely different applications. Not this material. It's interesting where the weight becomes interesting, and in your case, the weight is not interesting.
So
yes.
Did you consider the digital image correlation method to measure the mechanical properties of the material? Get the, for example, the Poisson radius in terms of the strains instead of the stresses, and to avoid setting to zero the stresses in one direction?
Yeah, but with optical method you have two options: video extensometer or laser extensometer. Right? So for the video extensometer you need a certain pattern. For the laser extensometer, not. But for the laser extensometer, what is the problem? You don't have sharp borders. I mean, with this, maybe it still would work a little bit, but with these open cell foams, which are showed at the very beginning, which are similar to trabecular bone, it's a big difficulty, because you do not have a sharp border for laser extensometers. Yeah, it's possible to do something with optical measurements, but it's not easy. It's not so easy. So if you would have a classical sample with sharp borders, you would take a laser extensometer, yes.
Yeah, laser.
And you could measure the contraction. Here it's because you don't have a straight line. So it's some kind of curved surface, and this makes it difficult for this evaluation. Yes?
In terms of application, you talked about medical use and replacement bones or something along those lines, is it?
Yeah, I mean, it depends how the structure looks. So if we have this structure from the beginning, where we have an open cell form which is close to the human bone, you could imagine that this is used like a skeleton, where bone could grow inside. Let's say part of the bone is damaged. this way. So if you have an open cell structure, and if you do not use aluminium, you use, for instance, titanium, or maybe other materials, bone to chrome side, and if you go a further step, if it's an absorbable material, after the bone has chrome inside, maybe the material could be absorbed. So these are the ideas of cellular materials as scaffolds for bone replacement. Either permanent, then we use titanium, or any bioabsorbable material which would be absorbed by the body after the bone has chrome inside.
So instead of perhaps focusing on trying to define the properties, would be to come up with a bone-shaped made out of whatever.
Sure, we are doing actually such investigations. What would be the best cell shape in order that the bone can grow inside?
And then take Bill's option of actually testing that in terms of comparing it to bone, in terms of strength and things like that, to say, yes, it's suitable for purpose.
Sure. In these biomedical applications, sure, different questions are interesting. So we would rather look for a stiffness which is quite similar to the bone in order to avoid this effect of stress shielding, where basically the bone is not growing but degenerating because of the different stiffness of the implant. Yeah. It's a different question, yeah. But because you can adjust so many parameters, it's a possible task to solve. Because you can use different base materials, you can use different cell shapes, and this allows us to adjust the stiffness to be close to the bone. So this will be the best implant, which has the same stiffness as the bone, or the surrounding bone.
And isn't that driven more by the production of material?
Sure, there are different manufacturing methods. So we have the material, the structure, and the manufacturing method. So nowadays we are talking rather about printing these materials, either as some kind of polymer materials or either metals. So we can even create much more predefined structures, which were 10 years ago not possible. So here you have a heterogeneous structure, because this is from the manufacturing process, yeah, to a certain extent adjustable. But with printing, you would have, or we have nowadays, completely different options to clearly define the shape of the structure. So the problem here is the heterogeneous structure. We have some kind of network, but it's very difficult to adjust it. But this can be nowadays solved by 3D printing of metals or other materials.
Well, part of the problem with any three-dimensional thing, soils, say concrete and things like that, are scale effects, and that you can do all sorts of tests on small scale, but then you start expanding, then you've got
there are a lot of questions involved.
Changes in characteristics and properties.
That's classical aluminium alloy. So what we made, we had, just to compare the influence of the size, we made a classical tensile test with around tensile specimen 10 millimeter diameter. So we got a stress strain diagram. And then we manufactured a tensile sample with 1 millimeter diameter. The stress strain diagram looks completely different. So it's not like, well, you know, the aluminium alloy, you know, which type of aluminium. You cannot take these properties because these webs are so small and the properties are extremely changing compared to the classical sized specimens. Yeah, this makes it interesting or difficult.
Any other question?
Yes.
Is this material being tested in bending and shear as applied to a simple beam?
Yeah, 3-point bending, again, as a standard procedure was used. So basically, all the classical testing methods are applied to these materials.
And does it have potential for use as, for example, beams?
Well, not as a beam itself, but as a core maybe of a sandwich plate which is used as a beam. So you cannot use it just as this material. You need normally some stiffening surfaces. Yeah, but in the sense that it's used as a core here, then it's a beam. Exactly. That's a typical application. Core of sandwich plates which are loaded under bending. Sure, the other, well, the classical, at least in aerospace applications, core material will be the honeycomb structures. But honeycomb structures have a certain drawback. Okay. They are definitely not isotropic. With these materials, well, they're heterogeneous, but on the macroscopic level, rather isotropic. And it depends on the application. On top, they have much better behavior under pressure or impact load. The honeycombs are not very good under impact load. These materials would be much better. But it's all the time important what is the application or what is requested. Let's say if someone is looking only for stiffness, yeah, take a steel, a classical steel. It's the best stiffness. But if you need a certain stiffness balanced with a certain weight, then it becomes interesting. But if people are looking only on one property, the classical materials are all better. If it's only stiffness, we take steel. No need to take this. But if you need stiffness paid off with a certain weight, then it's interesting. Or if you need stiffness combined maybe with some vibration damping, then it becomes interesting. So only if you look on different properties, these new materials can substitute classical engineering materials. Just looking on one property, all the classical materials are better. If you have a wider view, then it becomes interesting. Like heat insulation, vibration damping, acoustic damping, or whatever, plus stiffness, plus maybe the possibility to have some kind of, I don't know, integrated heat exchanger cooling system, because something can flow through these open holes. Then it becomes interesting.
I just wondered about its application in seismic in terms of being a damper as well, the structural member.
A damper?
Yeah, as in, I'm not sure what the seismic load will be and how large it will be, but as a damper, but potential to save the structure.
Well, there are some investigations done, and they show these materials show quite good vibration damping behavior. That's only what I can tell you. Therefore, some possible applications could be some machine tables, and to have it as a core of a machine table in order to reduce the vibration of a machine table. Okay, so damping properties are important, and people are working on it. But again, if it's just damping, if you have damping plus something, it becomes interesting. Maybe damping and lightweight. Okay. Or if you think about some robots, where you must move to a certain position and there should be no vibration, no movement, exactly at a predefined position, then it becomes interesting. With light, you can easily move the arm of the robot, and it damps the vibrations. So you can easier start or quicker start with the manufacturing process. But all the time is important. Consider different types of properties, and only then it becomes interesting. Light, movement, vibration damping, yes, then otherwise not. If you just need vibration damping, again, classical materials are all the time better.
That's the last question. I can still see the question mark popping up. I guess we need to do probably 5-10 minutes after this. If you want to catch up with Andreas asking a few more questions, feel free to do that. But I think I'm just probably going to conclude the presentation by Andreas for tonight. Thank you very much, Andreas, for your interesting presentation, especially with this novel lightweight material. And I hope we probably can find lots of application for this particular material in the future. And as a tradition, we would like to present a little gift from Engineering Australia. And thank you very much for your presentation, for your help, and for your support.
Okay, thanks
for tonight. Thank you very much, Andreas. Okay. And could you please join me in thanking? That's for tonight, and thank you everyone for attending this event. Next week we will have, I think on the 30th of September, next week on Tuesday, we will have a site visit at Fulton Hogan at their Omo plant. If you still keep the email sent by Engineering Australia head office, have a look at that for the detail. And the event will be free of charge, so you can sign up and attend, but the only limited places only for 30. Okay, they can take up for only 30 people. So have a look again. If it's still available, then you can still sign up online. And I guess that's pretty much for our September event. the next week, and then that's done. In October, we still have a few more events lined up, but keep an eye on the emails from me, mainly from the head office, and I look forward to seeing all of you again in our next event. Thanks very much. Thank you. Have a good night.